Welcome to today's lecture, which is on another segmentation method, and this particular one is called as active contours. Now you might be having a curious note as to why is there the term contour and then there is an activity over there because of its being called as an active. Now there is also another name for this one called as a snake's method. Might have heard about that one if you are doing some sort of other advanced techniques as well. Now incidentally, what comes out is that this is a quite interesting technique, because the contour over here is actually something which can flow along the different perspectives of the image itself, and then it comes down to a convergence, and from this particular attribute of the contour itself, it gets its name called as an active contour. Now without much of a leaving you into this whole dilemma about trying to sort of imagine as to what this might be, let me give you an example. So say that you are given down with this objective where you have an image and you are just marking down two nodes over there, two points over there, and say that there is some sort of a contour which is supposed to follow, and this is supposed to follow this particular line, and then these are the two ends of the contour. So there is the contour is not going to exceed beyond those lines or even exist anything beyond them, but between them. Now in general you will basically have a straight line if you are just given down 2 points, but here the question comes down as, can you fit down a model which is somewhat flowing along this particular curve over here, which is that bright line. Now this is basically a small snapshot of the ultrasound of your lever, as we had seen in the earlier examples on texture where you had seen the cross section of a lever ultrasound as well. So this is just the diaphragm over there, and you just have to mark down the boundary over here. So this is the problem. Now the question is well formulated as that, find the boundary given that there are just two endpoints, and then finally you should be able to get this sort of a curved line over there. Now in terms of an active contour, how it is defined is, let's say that there are basically two hinge points which are called as R0 and R1, which are the two edges over there. Now these 2 points will not be moving in any way, they will always remain static and concentrated over there. Now all the points between them, so if there is some sort of a contour, or imagine that initially you just had one straight line over there, and there are you can have certain nodes over there in these multiple points. Now the idea is something like that, if you have a complex curve over here, so you can basically define this into a summation of piecewise linear things. So basically a curve can be represented as small segments of small line segments which are just cumulative one beyond the other. So over here there can be one line segment linking R0 to RS1, there is another line segment linking RS1 to RS2, and like this, such that you approximate almost this curve over here. And these points RS1, RS2, RS3, RS4, initially they might locate somewhere over here, and then eventually they will be dragged in a way such that they can be located onto this particular curve over here, which is an attribute of the image. That is what all of this business about active contours is to do about. So you need to remember one thing in mind, that since it is called as an active, and that whole thing comes down from the fact that this contour is mobile. So the contour can move around over there, and since it has to move and converge at a point of time, so this necessarily has to be an iterative process, otherwise it will not be converging. So all of this, what we are going to do is to come down with an explanation of what to converge and how to converge, and since basically this has to move, so you will have to find out how to move, then how do you find out some sort of a force which will basically be drifting this contour in a particular direction, otherwise this might not come down to a convergence point over there. And also on top of that, you need to understand what is an energy over there, which is going to be minimum in case the contour is at the particular point. Okay. So let us start with the basic definitions. Now consider that there is a curve over here which is what you would like to approximate, that is the actual final state of the curve, and then assume that there are just 3 points given out on this curve. Okay. This is a very straightforward curve fitting problem, and let any of these points be called as RS. Now if you look over here, this R is a vector, so this R is basically an XY coordinate couple, just a coordinate representation. So every point basically is a representation of x comma y in this coordinate space, and S is basically a number which it denotes which particular point you are taking along this contour. So over here S is equal to 1, this is S is equal to 2, this is S equal to 3, and so on and so forth. So basically S varies in the order of the number of points you have on that contour. and these points are basically hinge points. So you can have infinite number of points basically between them, but these hinge points are what will be guiding as to how the contour can flow across on that image. Now from there you can obviously have a piecewise linear approximation between these points, and this dotted black line is the contour, which is an sort of very good estimate or an approximate estimate of the actual final contour where it should be lying down over there. Now if that is the situation, at a point Rs we compute something called as an internal energy. Okay. So this internal energy is basically a weighted summation of the first order derivative and second order derivative along this particular curve. Now look at this one, that we are taking a derivative along the points on the curve, along this parameter S. Okay, it is not an image derivative or anything, it is not a derivative of the grayscale intensity of the image, which obviously we use in a different point, but this is basically del r del s is a vector of del x at that position r s, del x with respect to del s I cap, and del y with respect to del s j cap. This is how this whole thing, this first term will be broken down into. The second term would appropriately be broken down in terms of a second order derivative as well, and then you need to take down the weighted summation of them. Now this first term over here is called as elasticity of the contour, the second term is also is known as stiffness of the contour. And imagine that you have a rubber band in your hand, and this rubber band is supposed to go down. So imagine that there is a plane surface on which you have a few pins and you have a rubber band, you have basically stapled the two ends of the rubber band over there, and then you have to pull this rubber band such that it goes across these pins over there. Now when it goes across these pins, you will see that the first term elasticity, it basically gives you what is the total energy which is due to the elastic force being applied on the rubber band over there at any point, and then the second term will basically give you the range of stiffness, which is like it is basically the derivative of the force which is being applied on that rubber band over there. And if like you reach an elastic limit and it is at the verge of breaking, then this force as such starts becoming 0. That is where it will come down to. Now from there, there is another force on every point which is called as E external, and this is basically the first derivative of the intensity of the image itself. So this F over here is basically intensity at this particular point on that image. So as your points keep on moving, as say this point, it keeps on moving from somewhere here till here, so the intensity over there will also be moving. So appropriately your gradient of the intensity, which is nabla of S, will also be moving. So and you are basically taking down the absolute value of that gradient over there. So this part comes down from the gradient of an image, the standard gradient of an image, which you can compute with a Sobel operator or a Prewitt operator over there. So this part is called as the external energy. Now the objective over here is basically that, say you have a curve which is denoted as C, and we define this as some sort of a cost function in terms of this curve, then this cost function of the curve is basically the integral of the internal energy and the external energy over the whole length of the curve. Okay. So basically the whole curve is divided into multiple of these S's over there. So you are just going to take this total summation over there and then integrate it along the curve length, and you will get down an energy proposition over there. Now this is how the energy or the state of a particular curve at any point of time is denoted as. Now from there we come down to the next part, which is a convergence criteria. Now as I said that initially what you are given is basically an image on which you are just given 2 points, and now you have to start with some sort of an arbitrary curve in between these 2 points, and then all the points in between these 2 points on the curve will basically be moving and coming down to a point. So initially it starts with something like this, that you are given down 2 points and then you draw a third point over here, and this is your estimate of the curve. Okay. Now given this fact, you start by minimizing the external energy and the internal energy along the length of the curve, which in turn will lead to minimization of this whole cost function, because if you can minimize internal and minimize external, you will end up minimizing this whole thing together over there. Now as this whole term reaches a minimization, you would see that finally it converges onto this criteria over here. Now eventually you know that if this whole integral has a minimum value, then since these are energy values over here, so they would finally have an energy which is equal to 0. Okay. Now, if you equate this minimization criteria, so wherever you have a minimization, you basically have the derivative of this is equal to 0. So, by solving that first derivative criteria, you would get down that in order to achieve convergence, you need to have this sort of a criterion established over there, which means that the first derivative of the elasticity function, which was my del r s del s as in the previous slide. So, it is basically first derivative of this one and the second derivative of my stiffness function together with the summation of the gradient over there, everything together has to be 0 such that I am able to achieve this criteria. Okay. Now, this particular equation over here, which is my condition at convergence, actually acts as the major driver in order to design something called as a solver. Now, solvers are basically when you have a mathematical model in which over time you can iterate certain thing and then come down to a convergence point. Now, look into this one. What you initially start with is basically 2 points and 1 point interpolated somewhere in between. Okay. Now, in the first iteration, this is where your energy criteria is found out. Now, based on that, you will be getting some update rules over there as well. So, we will be coming down to what those update rules are. Now, once you get an update rule, then you have a second position where you can move this intermediate point. Okay. Based on that, you will again get some update rule. Based on that, you will again be moving. You keep on moving until you achieve this particular criteria or this particular criteria, any one of them. The point when you are at a minimization position, you just stop over there. Okay. So, let us look at how this solver is going to work. So, imagine that this is the condition of the contour at so this is what it will be at the final spot, but you can imagine it to be at any intermediate point as well. Okay. Now, between these 2 points s minus s of I minus 1 and s of I, you can find out what is the distance between them. So, this is just basically the Euclidean distance between them, because these exist on a rectangular Cartesian coordinate space. Okay. Now, based on that, first you need to find out what is the first derivative of this r of si for each of these points. Now, you can compute this numerically with the estimation going down by the backward difference rule over here. Okay. You can employ the forward difference rule, you can employ the central difference theorem, any of them accordingly over there. Now, from that one, you can also compute numerically the second order derivative along the curve contour as well, right. It is not such a complicated task. Now, once you have all of these 3 computed, next what you need to compute is the gradient, which is for your external energy. Now, gradient for an external energy is a very straightforward computation, because you just take the derivative of the image along x direction, derivative along y direction, and then take the summation to get the total gradient energy over there. So, that is a straightforward computation. Now, once you have all of them and you solve it out completely, what you would get down is that the final update rule looks something like this, that say you start with the, so for any point s, okay, any of this si's over here, say it has a value of x in a superscript within bracket t, which is at a particular iteration over there. So, t equal to 0 is the starting point, t equal to say 10 or 15, whichever is the final position, that is your final end point. Okay. Now, over here what will happen is that you start with an initial estimation. So, say t0 is your starting point. Now, at this t0 you have your value of x t equal to 0, then over there based on that you also have your r of st for t equal to 0. So, you can find out this del of E of RST del x. So, this part over here is basically finding out the total energy which was computed and taking its derivative with respect to the x coordinate itself. So, this is the x derivative over there. Okay. Over here you get another term called as the matrix A. Now, this matrix A is a much larger and complicated matrix, and where this comes down, and this I is basically the identity matrix. Now, this A comes down by basically writing down a linear algebra equivalent of the earlier minimization energy functional form. So, if you write it down, expand it out completely, you can find out the details in the actual text where it suggested down for more of it. Now, for most of the solvers, this part over here is just a matrix which is kept constant. So, this is constant over a complete image, this does not vary over there, and this gamma over here is basically an update coefficient which you would need. So, now what you need to do is, now that you have this matrix, you need to subtract this gamma times of I, which is basically a diagonal subtraction over there, and then take its inverse, and then basically multiply that inverse with this particular form over here. Now interestingly, what would come out is that this matrix in its inverted form multiplied by this whole thing over here is going to give you a scalar value, and that is your updated version of x t. Okay. This A matrix is also called as the state matrix of this update rule equation over here. Now similarly, you can also update the other part of it, which is your y coordinate, because you need to update both the x coordinate and the y coordinate so that the point can move appropriately in space. Now once you are able to have both of these update rules solved and get down a complete conformity of them, comes down the fun over here. Now say that this is an example where we are looking at a angiogram in blood in the heart. So it's a cardiac angiography image which you are seeing over here, and this is one of the blood vessels on which the contour has to snap down to actually. Okay. Now if this is the contour which you initially start with, or say this is the contour you initially start with, in either of the conditions it would actually come and snap onto this contour which is close enough over here. So you can start with a point which is very far off, you can start even with a very weird shape, and that will come down. And the reason why it comes down is because you have these gradients which are the external energy over there. One is the internal energy which just restricts the points from flying away, so that it looks like a very conformative contour over here and it does not fly away. The other point which you need to look over here is basically that it again restricts itself to the actual shape of the object on which you are trying to look over here. So this external energy or the derivative over the image basically gives you the idea about the shape of the contour on which you are supposed to lie, and until you come down onto this one you will never be at a minimization condition in any way. So this is the beauty of active contours, of how they can snap down to the actual model where they are supposed to go. Now based on this, so this is not just where it ends, because you can look into one major problem over here is that say that you have a very short object, short span of contour on which you want to fit down, then and you are very close to the actual closing criteria, then you can snap down very easily. But say that you have something like a lesion, okay, and you have drawn a closed contour which is a small circle which is enclosing that whole lesion, and now this circle is supposed to snap down onto that object. But if you just use this kind of energy function as we have used only for an active contours with the snakes model, it will never be going down and snapping onto this object conformatively. So most likely it will just be dangling somewhere in between, and there are also conditions that if the contour is much farther apart from the actual point where it is supposed to snap down, then it can start wobbling as well. Now in order to get rid of that, we have a new kind of a model which introduces another force, which is a drift force, and this is called as a balloon model. Now what it does is, assume that you have some sort of a balloon which can constrict itself to a volume of 0. So there is a balloon which you can inflate, and then it can constrict itself. So now this inflation will be dependent on what you are going to fit. Now imagine that you have a balloon and you are blowing it out. So generally it will be a convex spherical shape on which it blows out, right. So there can be different kind of balloons which blow down as cylindrical shapes as well, or in different kind of artistic shapes. Now if you are not blowing this balloon or trying to fit this balloon inside a rock, so the rock is inside the balloon, then this balloon is basically going to stick to the surface of the rock and follow down that contour, and this whole thing happens because the balloon has a natural tendency to constrict itself. So if it has a natural tendency to, any contour which has a natural tendency to constrict itself is definitely going to follow down the normal at any point, so the normal vector which is pointing towards any point, and that is where we get down this new energy function. And what this does is, there is an external force which is supposed to be applied over there, and this external force is a weighted function of the normal force and the external energy over there. So while the external energy is trying to drift apart and pull the balloon, to pull the contour to come outside, this force in the normal direction is forcing it in the opposite direction. You can look at the sign changes on the vectors over here. So this is what basically signifies what is going to happen over here. Now basically what you try to do is, if you look at this particular contour over here, then the normal will be something which is forcing itself inward, right. So you have one force which is on this side, another force of tension which is on this side, so your normal force is which is pulling it inside, and the external energy is something which is pushing it on this side. Now it will come down to and converges in that kind of a criteria, and these are very useful in medical image segmentations when you are trying to look into a very closed object and a closed contour in totality. So for one of the examples you can look over here. So initially, so this is about a CT of the upper abdomen, and you have a lesion over here somewhere around your lungs, and now the objective was that you draw an initial estimate of the contour which is over here, and you are supposed to snap it down to this actual lesion, and this can be used for basically finding out what is the lesion area or the lesion volume over there and other characteristics along the edge or the perimeter of the lesion. Now if you are not using a balloon model, in general case you will have a contour which will just be spherically located over here, or there are even chances that it can actually blow out and enclose this part over here, which is not that actual lesion which is supposed to be encapsulated, because if you look over here, this is supposed to drift down and come down over here as well. So that is a wrong thing. Whereas when you are using a balloon, since it is always trying to retain a very convex shape in itself, it is forcing itself inward, the tension is pulling itself inward, and the force of intensity is pushing it outward. In that case you would always find out a conformity to become convex over here, and that is where this converges to a perfect condition. So with a balloon model, your active contours are in a much better position to actually converge down on a particular point. So with that we basically come down to an end of this short lecture. You can read about more details in this particular book by Tonyson, Guide to Image Medical Image Analysis, on chapter 9, which is on active contours and active surface models. So although we are concentrating only on active contours which exist on 2D, but obviously you can extend this to the 3-dimensional space. In case you are on 3D space, you will have something like a surface which is the boundary of objects over there. So you can extend all of these criteria to your 3D if you have a 3D object, and if you have 3D data sets on which you try to do, in that case, since everything is extended onto 3D, this contour now boils down to become something called as an active surface, and that is where it converges. So all starts with the snakes, it goes down to balloon models, and then you have some more advanced topics like level sets. You can have other techniques based on level sets as well, but snakes as such and balloon together are some of the most robust and most widely used techniques for segmentations as far as active contours and surfaces are concerned. So with that we come to an end, and thank you.